I'm sorry, Georgia, you tried to help and I told you no, and then that's right. Okay, starting recording now. So one of the things that we had been talking about when we left off in the last class is the kind of relationship between log odds, and probability. So here I've tried to show in the updated workbook online the relationship between these three things. The logistic regression is linear in the log odds, and you can see that on the left side. In the middle is the odds, and you can see that once we take the log odds and we remove the logarithm, it then becomes an exponential function. And it's kind of hard to see because the red line is an exponential function with an exponent of 1, and the blue line is an exponential function with an exponent of 2. So you can see how quickly something that's linear over here, if I just do a simple transformation, becomes something that's exponential here. And then when I convert from the odds back to the probability scale, I get this looking thing. And this thing on the right is the logistic curve. So that's the thing that we're taking from the log odds. We transform it all the way to the probability. Okay, so this is what I was trying to show yesterday, and I've cleaned it up. I'll probably end up shrinking the graph a little bit vertically because this is kind of gross, and it looks different on my computer, but that's what I was talking about. I know, Sophia, yet another problem with Blackboard Collaborate Ultra. So the main point is that the left pane shows the log odds, and the right pane shows what we're constructing when we make a logistic regression. So we're just doing a linear regression in the log odds on the left, and then transforming it back to the probabilities. And you see how something that's a line on the left, after doing 2 nonlinear transformations, gets us to something that looks like that S-curve. The one in the middle is just the raw odds, so not the log odds. I've exponentiated it. So it's like you're doing a nonlinear transformation in both cases. So I'm going to move on from this kind of stuff. And the point of today is to kind of close the loop on working with binary data. So I'm going to reshare on my RStudio. I guess I should say fig height equals 4, and that'll probably look better in the future. Okay, so the very last part of the lecture, or of the workbook that you need to know, right? So when you get these kinds of curves and you get probabilities, these are numbers between 0 and 1. So we're generating some prediction for whether or not we think y is 0 or y is 1. But both of the models, can I zoom in a bit, please? Yes, I'll zoom in further. Is that better, Finn? So it's kind of hard to balance. Okay, cool. So both of the models that we've talked about before, the linear probability model, which remember is just a linear regression with binary y as your outcome, and the logistic regression give you a predicted probability that y is 1. Okay, so both of them do that, a predicted probability that y is 1. And then if you remember the linear probability model, if you just do predict the linear probability model, you get back the probabilities that y is 1. And in some cases, you'll get probabilities over 1, which is why we move to the logistic regression. In the logistic regression, we used predict to see those probabilities. Well, in fact, if you just predict by default in the logistic regression, they're not probabilities. They're log odds. In order to get log odds out of your logistic predictions, you have to do type is equal to response. And then you get probabilities. So we talked about this yesterday. Our y is in terms of the binary variable. It's 1 when your friend thinks a wait is too long, and it's 0 when your friend thinks a wait is not too long. But our predictions, both for the logistic regression and for the linear model, are in terms of probabilities. So how do we move from probabilities to our binary classification? Well, if you remember from the very first lecture in this chunk, we do that using a threshold. So one really reasonable thing would be to say, okay, working with the linear probability model, if your probability is greater than 0.5, I'm going to say it's a long wait. And if your probability is less than 0.5, I'm going to say it's not a long wait. Okay? So if I take the probabilities from the prediction and I say, okay, if you're greater than 0.5, then you are a long wait, I get something that looks like this. It just takes those probabilities and classifies them into a binary outcome. Does that make sense to folks? The models naturally are generating predictions in terms of probabilities. And in order for us to actually assess whether or not the model is predicting correctly, we then have to take those probabilities and turn them into binary 0 or 1. So if I have the times data and I have these trues and falses, I could say add a column, which is the prediction, where I say predict, let's say the LPM, the linear probability model. And then I get the probabilities as a new column. I'm going to move this up because we're not using that. And then I could mutate it again and say prediction LPM binary is equal to prediction LPM greater than 0.5. Okay, does everybody see that? If I'm working with this in a tidy fashion, I might do something like this. Now, how do I assess the accuracy of classifications? Well, if I think about it in terms of making a guess, then I want to know how many times my guess is wrong. In a standard linear regression, on a continuous y, we use things like r squared, or we use things like the root mean squared error. We might look at the residual. But in a binary model, we're kind of more interested in the prediction accuracy than anything about the residuals, because we never actually observe the true probability that y is 1. We just observe the fact that y is 1. So most of the time when you're working with classification-based models, you're interested in the accuracy of the classification. So if you see here, now I've used the linear probability model, and we'll get to the logistic model in a second, exact same procedure. So I've used the linear prediction, or linear probability model to give us the probability that y is 1. And then I've said, if that probability is above 0.5, then we're going to say it's a long wait. And that seems reasonable, because if my predicted probability is above 0.5, it means that our model set is saying that it's more likely than it is not that we've had a long wait. Is everybody with me so far? I should phrase that differently. Is anybody lost yet? Okay. So let's look at this prediction. Our model gives it a 59% chance of it being a long wait. So that means we predict it as being a long wait. Does everybody see that? So it has a 59% chance. So it's predicted as a long wait, because that's bigger than 0.5. However, it was actually considered to be a short wait. This type of error is called a false positive. If I predict that something is true, or 1, and in fact it's 0, I am falsely detecting a positive result. Now, you've heard this language before. We've talked about it in terms of hypothesis testing. So you should kind of be familiar with the concept of a false positive. It's when your algorithm for prediction tells you that something's happening when in fact nothing happened. So our model says this is a long wait when in fact it was not a long wait. So that's a false positive, and that's one kind of prediction error. You can see this is also a false positive. Now, look at the last prediction for the milk thistle. This is a false negative. Sorry, was the 0.591 the predicted probability it is too long? Yes. So this prediction LPM is the probability that our model thinks the wait was too long. So yeah, perfect. No problem, Georgia. So this is the probability that our model gives that the wait is too long. And then we've said as an arbitrary kind of step that if this probability is greater than 0.5, we're going to say the wait is too long. And that results in this being a false positive, and this being a false positive, and this being a false positive. Does everybody see that? Because they're false, in fact, when our model says they're true. Okay. Now the very last prediction error here is what we call a false negative. So your friend thought row 17 was too long of a wait. However, our model assigned it a probability of only 0.39. So it decided, because 0.39 is less than 0.5, that that is going to not be a long wait. It's going to predict false, because the probability is less than our threshold. Does that make sense to folks? Does everybody see that? So this is a false negative. Everything else in our prediction set is correct. This is true, and this is true. We call that, when the two are in agreement, a true positive. And when they're both directly false, we call that a true negative. So you can actually arrange this in terms of a cross tabulation. where you have your long weight and your prediction LPM binary. Oh, geez. Am I not able to? Oh, right, because it's not tidy. And that doesn't work. Okay, so crosstabs are a bit annoying. So let's group by the long weight, the prediction LPM binary, and say summarize n equals count or sum. Whoops. Oh, sum. I need count, sorry. Fuck. Okay, we're going to do this using X tabs because cross tabulation is kind of annoying in the tidyverse. I say this in the lab. So we're going to use X tabs to give us cross tabulations because tidy tabulations are annoying. So what I'm going to do is I'm going to summarize the number of long weights that are also prediction LPM binary, data equals LPM predictions. Long weights, of course, it's not long weights. Okay, this is what I'm looking for. So this is what we would call a cross tabulation. And you've seen this kind of thing before back when you were doing chi-square tests in the first year. For those of you who that just triggered a panic attack, don't worry, you're not going to be doing chi-square tests. We're just going to be looking at this as a way to summarize the prediction errors. So remember, LPM predictions has a couple of true positives, a couple of true negatives, a couple of false positives, and a couple of false negatives. If I were to count up the number of each of those types of things, I would get this table. So the number of false values that are predicted as false is 2. That's these 2 rows. The number of false values that are predicted as true, which are false positives, are 3. So that's 1, 2, 3. The number of true values that are predicted as false is 1. Whoops, that very last row. And finally, the number of trues, the number of long weights that are correctly predicted as long weights is 11. That's everywhere where it says true in both of these prediction columns. Does everybody see that, how we get here? I'm just making a cross tabulation of that set of predictions. So this little crosstab, where you have the correct value on the y and the prediction on the x, you can also flip it, it doesn't necessarily matter too much. But basically, this cross tabulation that compares the observed classifications to the predicted classifications is called a confusion matrix. And this is because it characterizes the confusion in your model. It shows you how many times your model confuses a false with a true, and likewise a true with a false. Some of you who have done more work in remote sensing have seen this kind of thing before when you're classifying land cover. There, you can use it in a multi-class context to say, we think that this grassland is actually a forest 20% of the time. So the terminology of confusion matrix comes because you're showing where your model is basically confusing 2 classes. And here, since we only have 2 classes, it's just the true positives and false positives, and true negatives and false negatives. So in the assignment, I ask you to make a confusion matrix. And I personally think the easiest way to do that is to use the crosstabs. So xtabs or table, both of them are functions that allow you to build a cross-tabulation or a contingency table. And I think that this, using xtabs, is the easiest way. And you can see that in the workbook as well. I do that for you. Now, here comes the fun part, or maybe the interesting part. So in my LPM table, I've used a threshold of 0.5 to make my classifications. And I've said any probability that's above 0.5 is going to be true, and everything else is false. Okay. Do you think I can pick a better threshold that would give me better accuracy? Can I reduce the number of false positives or false negatives by picking a different threshold? And the answer is yes, I can. If you look at the errors that we make, there are only 4 when we pick a threshold of 0.5. We see that our one false negative has a probability of 0.39. And we see that our 3 false positives have probabilities 0.59, 0.67, and 0.66. So if I wanted to move my threshold to try and correctly classify these different observations, then I could increase the threshold and change these false positives to become true negatives. Alternatively, I could try and lower my threshold and convert this observation into a true positive. So I can move that threshold around and say, okay, well, I actually need to be more certain that something is a 1 in order to classify it as a 1. Or alternatively, I could lower the threshold and say, okay, I'm okay with things being less likely to be a 1 and still counting them as a prediction to be a 1. How do we do that? Well, when we make this kind of mutate here, there are 2 steps. I'm getting the probabilities, and then I'm making a classification. So just to make this a little bit more generic, I'm going to call that prediction, and I'm going to call that classification. Okay. And this comes with a threshold. So putting it in more abstract terms, my threshold is 0.5. Same thing. So when I pick a threshold, I'm saying all of the probabilities that are above that threshold get classified in the same way. If I change the threshold, it changes the prediction. So now I've set the threshold to 0.6. In doing that, I have changed the balance of true positives, false positives, true negatives, and false negatives. I have converted row 6 into a true negative, but that had a cost. I now am saying row 5 is a false negative. Does everybody see that? I've picked up one correct negative with the cost of gaining a false negative. By changing the threshold, I'm changing the classification decisions. I still have these two false positives. If I keep increasing the threshold, let's go to 0.7. Now I've really changed it. This remains a false negative. We still have a true negative, but now we've also incurred many more false negatives. Is there a way to set thresholds for separate pubs? Josh, you could, yeah, but it's typical in classification decisions to try and pick a common threshold, because our hope is that we've taken care of heterogeneity in the pubs in our model already. So we don't try and pick different thresholds for separate pubs. You could do that in theory, and there are approaches that go ahead and do that. But in logistic regression, we generally pick one threshold for everybody, because the model, not the threshold, should account for that. Excellent question. So I could, let's say we do this to show you these things side by side. I'm going to say let's say I have three types of classifications. Strict, where I'm going to say it has to be greater than 0.75. And then let's say I have normal, which is going to be a prediction greater than 0.5. And then I might have lax, which is prediction greater than 0.25. So the strict rule, when we set our threshold to be really high, has more falses. The lax rule, where we set our threshold to be really low, has more trues. And that's just because we're taking each of these predictions and we're just slicing them right at a particular probability and saying everything above this is true and everything below that is false. In the assignment, I ask you to look at a couple of different thresholds and tell me which ones have better confusion matrices. So if I said LPM predictions, because we're working with the linear probability model, then I could say X tabs is a function of long wait plus strict, and get the strict classification matrix. I could do that again for normal and get the normal threshold classification matrix where it's 0.5. And then I could look at the lax classification matrix where the threshold is 0.2. Now, just comparing these things, our strict classification has no false positives. How do I know that? Well, looking at this row, there's a 0 for the number of things we think are true that are actually false. So the stricter threshold is going to say, okay, you need to meet more and more conditions. You need to be more and more certain that something is actually a positive in order to say it's a positive. So increasing your threshold tends to reduce your number of false positives. All the way on the bottom, you can see that our kind of relaxed threshold says, okay, you need to only meet a really low bar to be a positive. And in this case, it has no false negatives. The classical kind of way that people talk about this trade-off in classification is disease testing. And there, it's more often than not the case that you're trying to minimize the number of false negatives. These would be the people who a test says don't have a disease when they actually do have a disease. Exactly, Cracker. This is really important for COVID testing. The false negative rate tells you how many people actually have the disease, who actually have the disease, are given as not having the disease. So here, our false negative rate is 0. And I get that by taking this value and dividing it by that value. Well, the sum of that row. So it's the number of truths that our model says are false. Percentage. And then if I were to talk about the false positives, I would be talking about the percentage of falses that my model says are true. So in this case, 3 out of 5 falses are predicted as being true. In that case, our false positive rate is 60% for the lax criteria. In the strict case, our false positive rate is 0 because all of the falses are predicted as false. But our false negative rate, the percent of truths that are said to be false, is 5 over 12, which, doing some quick math, is 41%. Bronwyn asks, the false positive rate is the same for the normal and the lax threshold. So does that mean that the lax threshold is better? Depends. If you're more concerned about false positives than you are false negatives, then your decisions may change. Now, the accuracy is generally taken to be the percentage of all of the predictions that are made correctly. So in this case, the normal threshold has 13 correct predictions out of 13, 14, 17. So 13 over 17 is a 76% accuracy. The lax classification manages 14 out of 17. And the lax classification also has a lower false negative rate and the same false positive rate. So answer that yourself. Do you think the lax threshold is better than the normal? Which test would you rather take to figure out if you had, I don't know, some disease? It's probably the lax threshold. Up at the top, what's the accuracy of our strict threshold? Well, it's going to be 5 plus 7 divided by 5 plus 7 plus 5, 14. That's 70%. So it looks like as we lower our threshold, we get better accuracy. But that comes with a cost. We're going to predict that our friend thinks that a wait is going to be longer or too long too often. We're going to be trading false negatives for false positives. And in doing so, we might get better overall accuracy. Okay? So the point of this is to show you the concepts that are involved in assessing classification. Generally speaking, where you put your threshold is going to depend on what you care about. If the point is just overall accuracy, the best classifier out of these sets sets our threshold somewhere small. In terms of the accuracy. Now, if we're trying to minimize the number of false positives, we might want a stricter threshold. That comes at the cost of accuracy. So it's kind of like a pick your poison situation. There's a trade-off here. There's a challenge question that talks about building these things called receiver operating characteristic curves. They're normally very simple to build using code, and they directly represent this trade-off, depending on where you put the threshold. But the main point is, for the assignment, you need to be able to build these cross tabulations called confusion matrices, and you need to be able to interpret them. What does this row mean? What does this row mean? What does that column mean? And what does that column mean? So as long as you can do that, as long as you can compute the confusion matrix based on a threshold, you'll be able to do just fine in that last little component of the assignment. And that's it. Just to show you, if we're working with our logistic model, I still need to say type is equal to response, but then everything else is the same. Whoops, I should probably not save that as LPM predictions. I should save that as logistic predictions. Everything else is the same. However, if you do pick a different the two kinds of models will generate different classifications at the same threshold. And that's because their probabilities will be different. So a logistic regression is going to give you different predicted probabilities than a linear probability model. So because of that, your classifications could actually be better in a logistic regression than a linear probability model. But you still have the same process by setting the threshold at a particular value and classifying all observations that are above that value as positive and everything below that value as negative. Georgia asks, which false and positive is the prediction and which is the observation in the confusion matrix? So when I build it like this, the confusion matrix where I put long wait first and then the prediction second, let's do this for the logistic. If I put long wait first and lax second, then this describes the number of things that are actually long waits, and this describes the things that the model predicts are long waits. So if I put actual first and then predicted, the confusion matrix is read as actual in rows and predicted in columns. If I reverse that, then it flips. And as long as you interpret it correctly, I don't care which direction it is. I find it easier to think of it in terms of the truth on rows and the predictions on columns. But you can also put the truth on columns and predictions on rows. Okay? And just to show you, sometimes, you know, that's the logistic, that's the LPM. But for some thresholds, they might be different. Okay? That's because the probabilities are different. So that's all I wanted to show you today, is just how to make these confusion matrices. That's the last little key to the assignment. Everything else is just linear regression, and there's only that one question on logistic regression. Okay? So if you have any further questions or any concerns, I'll be around for the next hour and 15, and we can chat. In addition, Tom and Lenka are around as well, and they're more than capable of providing assistance. So I'm going to build the breakout groups. Well, first, I'm going to stop the recording.